Okay, class, welcome back. Last time we discussed the propositional logic, and we saw that propositional logic, it consists of symbols, and the it consists of symbols, the meaning of those symbols, and then the sentences that are created using those symbols. So three things we saw over here in this logic. We saw many examples, and then we saw basically that in the propositional logic there are three main things that it is made up of. The sentences, you can say, they are made up of symbols, the constants, and the operators. And in general, we discussed that propositional logic itself, it is a logic language, and the whole language, it is based on three things. The syntax of the language means the grammar. The semantics mean the meaning of those sentences that we create, and then the entailment. Entailment means that existing sentences, you use them to create new ones. So we discussed all these things. We saw the syntax. So we have these five operators in this language. Then we saw the B and F form, and B and F is used to represent the grammar of any language constructs. So here it is used to represent the grammar of sentences. We saw also the precedence that is used. The order of precedence, it is same thing as you see the precedence is also used in other normal programming languages. And then we saw the semantics of the language that are done using the meaning of the sentences. They are clarified or they are declared using the truth tables. So we use the truth tables. I told you that you will not be using true at the start. So please use the same logic for the whole class. It should be like you did in your logic design course, starting with 0 0, then 0 1, and the last one is 1 1. So use this notation, not the other one. So I explained that if you want to represent some complex sentence, in that case you will define all the parts of that sentence one by one and build on those complex sentences slowly. Clear? So here was some of the examples. This was the truth table. I asked you people for a small quiz, and many of you have attempted it in the group. So here we will try it, and you compare your answers yourselves over here. So let's see. You have got a P and a Q, and you have P and PQ. P implies Q. So let me, I don't have enough space, so I will put over here P and Q, this one, P implies Q. So P implies Q will be true. Now P implies Q, for me, this is the only tricky operator in this whole language. Okay. So what's the trick over here? P implies Q. When P is false, you don't care about Q. So when P is false, you don't care. When P is true, then you will check that Q is true or not. If Q is false, then this sentence is not correct. Okay, so overall this is the answer. P implies Q. Now you take the AND of P implies Q with P. So it will come out to be false, false, and false, and only true option is the last one. Okay. So this is one representation. Now they have given over here another one. So I will again do it in 2 steps. Always in the exam you have to show all the steps. If you don't show all the steps, it means maybe you have tried to memorize things, or you are cheating it from someone. That will cause you to lose marks. Be careful. You have to show all the steps so that I know that you understand it. You do it yourself. So I will write over here on the side, but in the exam you will write at the same place. not P and not Q. Okay, I don't have space over here. So not P is true, true, false, false, and not Q is true, false, true, false. Okay, so this is not P and not Q. Now I will write over here not P or not Q, or not Q. Okay, so I will write it over here. So not P or not Q, so I will take the or of these two. So when I take the or of it, if any one is true, the output will be true, 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 and the last one is false, so it will be false. So this is not P or not Q, and when I take the inverse not of it, so it will become false, 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 true. Now remember one thing, I emphasize this, very important. It is important that even you understand it, still you practice it. It looks very easy, especially when you are observing someone else doing it, but you can always make mistakes until you do it yourself. So open up the book. You already have the book. In the book, at the end of the chapter, you will see examples for this. Okay, so most of the times I give the exam question also from there, so you just have to go there, you practice with some examples, not only the examples in the slide. Go to the book. I guarantee you that there is one exam question from this. There is a exam question from this in the final exams. Till now it has happened. I don't know for the next, but till now it has happened. Okay, so this answer comes for me. So you can say that overall this is my equation number 1, which is here, and this is equation number 2, the second part. Now I have to find out if these 1 and 2, do they have an no, equivalence relationship. Here, remember, what does equivalence mean? Equivalence means that they are 100% same. True, true, false, false, everywhere. So when they are equivalent, they are 100% same, I will write true. So false and false, it is true. Second step, false and false, again true, again true, and again true. So overall, this is the answer that comes with me. So if there was another question asked, in this question I only ask you the truth table. Okay, so you have to write down the truth table for this sentence. Okay, another question, if it is asked in the exam, that write down if it is a valid, satisfiable, or unsatisfiable. So this sentence is valid. Clear? If I ask about sentence number 2, is it this one, is it valid? So no, it is not valid, it is satisfiable. So I told you most of the sentences are normally satisfiable. Clear? So this is it. This is your first solution. Make sure you did the same thing, or if you did it differently or wrong, make sure you understand it from here. So here is another question. Now this is a little bit more tricky. This is something opposite. Okay, so I explained last time that these are the bullets, they are not minus sign. Okay, so for this, the question is that what is the value of these symbols if I say that these 3 sentences, they are true, all of them are true, means that they are, let's say, part of some knowledge base. So anything that is part of a knowledge base for some robot, it means that robot always holds these sentences, only then they can be part of the knowledge base. So these 3 sentences are part of the robot knowledge base. Now I ask, the question is, what will be the input values? For example, there are sensors. So what are the sensor values which make these sentences true? Okay, So for this purpose, and there is no fixed rule from where you will start. You will try to start from the sentence that is the smallest. So over here, if you see, the smallest sentence is a B. So just imagine when this sentence will be correct or true. It will be correct when B is true. So when the B input is true, only then this sentence is correct or true. So B will be definitely true, because we already said that these three sentences are true. So if following three sentences are true, what will be the 5 symbol values? So B value will be true. Okay. Now B is given. Now what next to do? Now if you see, look over here, the first sentence. Now we know already that B is true. So based on that B, you will see the first part of this sentence, the antecedent part of this sentence, the one that comes as the event, the trigger. So that part over there, there is a B, and B is already true. So when B is true, we don't care, because there is an OR gate. So OR operator, we don't care about E. So B is true, that means directly A is true. Only then this sentence can be true. So we don't care about E. So A is true. And then you continue. When A is true, it implies that J and M both are true. So J and M will also be true. Now only one thing is left, and that is E. Now in the first equation, first sentence, if you put E equal to false or E equal to true, in both cases, the sentence will still remain true. So you don't know what the value of E is. So in that case, you will write over here unknown. So make sure you understand it, and I hope you all solved it like this. So int element we discussed last time. So remember in chapter 7, I just want to repeat this important thing, very important concept, that each row or each instance in the truth table, it is called a model. This is the definition of model. Okay. So when I am evaluating some sentence, so the knowledge base contains this sentence. So only those sentences I will say that they are the model of this knowledge base which are true. So only these two and these two. 4 sentences, I will say that there are 4 model for this sentence or this knowledge base. Okay. So this is it. And what is the model checking? Model checking we saw in the last chapter, I think, and also over here, I think somewhere. So model checking basically means that you check all the possible values. So all the possible values where your knowledge base is true, you check one by one, put the value of, for example, this is your first sentence, this is your first model where knowledge base is true. So you check which values of input make it true. So they are A equal to false, B and C are true. So you will plug these values into the alpha new sentence and try to see, is it true? So model checking means that you try one by one all the models already which are valid. In the invalid models you don't try. The one that are not correct for knowledge base you don't try. So model checking, it means that you check all the models one by one for your knowledge base and sentences. Okay. And this is a time consuming task. Only here you have only 4 models. But if you have 100 elements or 100 symbols, then just imagine you can have maximum 2 power 10, 2 power 100, sorry, 2 power 100 maximum number of models, which is huge, very, very big. And it is not possibly doable. So that's why this the complexity over here is 2 power n, which is exponential. So the growth of this function or algorithm is exponential, which is too much time taking. Clear? So always we need some sort of smarter way to find the inference, to do the inference, or for the knowledge base and the new sentence. And model checking, it is available, but it takes too much time. It is not feasible. So we saw this. We saw these three things: valid, satisfiable, and unsatisfiable. I gave you some examples. Now here they are. So let's try them. So P and not P, P or not P, we discussed already that if you will make a table in the exam, if you are given such a question, you have to make a table always. Okay. So you will write down. So let me draw it again. So here it is. So you have only one variable P, and you will write down not P. So P has the two values, start with false and true, and not P has two values, true and false. Okay. So first, so let me write over here 1 and 2. So I will try two of them over here. The one equation, I don't write it here. So it will be P or not P. So false or true, it will be false, and the second one will be also false. Whereas the number 2 sentence, it will be false and true. So false, sorry, the first one will be or, so it is true. And this is also true because there is OR gate. OR is always true, so here it will be false. Okay. So overall, your sentence number 1 will be true, true, so it will be valid. Sentence number 2 will be unsatisfiable. Okay. What about 3 and 4 and 5? So let's see. We don't have enough space over here. So P or Q or P implies Q. So let me try it. So here is the, I don't have enough space. I don't know what to do. So I have two variables P and Q. So bear with me because I don't have enough space. So P, Q, false, true. So always use the same sequence. True, false, and true, true. Okay. So P and Q. So I will write over here sentence number 3. When I want to solve it, remember to solve the complete sentence, first I have to write this down. So P equivalent Q. So P equivalent Q will be true over here, and false, false, and true. This is it. Then I will write down the last one, which is the sentence number 3. So sentence 3 will be this P equivalent Q or with P and or with Q. So it will be, when I am doing the ORing, most probably one of them will be true and the result will be true. So overall, this is a valid sentence. Okay. Now I will go for the other one. So let me erase the things from here. So I will again write down over here. This time it is P. So to solve number fourth sentence, I will write P implies Q and Q implies P. So P implies Q. It gives me that when P is false, I don't care. And when P is true, then Q should be true. So it is this thing. Whereas when Q implies P will be the opposite case. So when Q is false, I don't care. So Q is false in these two locations. I don't care about P. When Q is true, P should be true. So this is the result. Now number 4 sentence, what I will look over here is the OR of these two parts or these two clauses. So ORing of these two things will do true, true, true and true. So overall it is also valid. Okay. So this was it. This is what we want to do. The last one, to solve the last one, again this time we have 3 variables. So I will start writing here. I don't have enough space above. So I will write these variables: food, drink, party. Okay. So food, drink and party. If you have 3 variables for your exam, first of all start by writing them down all. Before you do any solution, write them down. What are the possibilities? So this is it. False, true, false. So how many possibilities you will have? Yes, 2 power 3, which is 8. So false, true, true, and true, false, false, and true, false, true, true, true and false, and true and true and true. This is it. So this is for 3 things I have written in abbreviation: food, drink, party. Okay. Now I will write down over here food implies party. F implies P. So it is I will look at first one and last one only. So F is false. I don't care. So okay, false, false. So whenever F is false, I will not care about P. And when F is true, P should be true. So this is it. So food implies party. That's it. The second one is drink implies party. So D implies P. So this time second and third symbol I will check. So true, true, false, true, and true, false, and false. No, that one is true. Sorry. So I have to go and erase it. And these things get very tricky very quickly. Be very careful in the exam. When you are solving, try to give this question plenty of time. Okay. And be careful. So drink, and when you do it, at least check 2 times if you have done everything wrong, right. So drink implies party. So when it is false, output is true. When it is true, output should be false, true. So here it is correct. And when it is false, here it should be true. Okay. And when it is true, this is false, and this is true. So this is the second one. And what about the third one? I think I have to do it this much at least first. So then I take the, so this is my first part of the equation. I don't have enough space, so let me call it A. So I will write over here the A, or I will write it here, I think. So don't mind it, but I don't have any other option. So this will be the OR of this and this. So ORing of this and this will be true, 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 and I think all are true except the second last. That's it. Okay. So this is my A. Now I will erase this side and I will do the rest of it. So I have to erase this side. So here the one is food and drinks. So food and drinks, just and operator. So your logic design concept should be clear if you want to excel in this part of the course. So here it will be false, false. So it's an AND gate, so basically it will be false most of the time except when both are true. Okay, that's it. This is food and drinks. And the next one is food and drinks implies party. So check if this thing, it implies the P. So both of them are very near. So I will call this B. So I will write over here B. So B is, I will say that food and drinks, whenever it is false, then I don't check output. Then it's true already. So that makes things simple. Now for the last two cases. Here when a food and drinks is true, now the party should be true. If it's not true, then there is problem. This is the case. Okay. And finally, A should imply that B. Okay. So if A is true, B should be true, and that is the case. When A is false, I don't care. So in that case, the overall this equation number 5, it is all true. Okay, and it is a valid sentence. So this was a little tricky question. I hope you did it right. So this was it. Now come to the last part of the course. We will finish it here. We will not go to these complex things, and we will go to the next one, which is the first order logic or predicate logic. So in lecture number 9, first order logic, we will just cover it very briefly. So you have seen previously that propositional logic is declarative. Declarative means there are two types of languages, either procedural or declarative. Procedural are like sequential, whereas declarative, they are each sentence is independent. Okay, not depending on anything else. Like some mathematical formulas, not all. In mathematics also there are some functions. For example, you write steps of formulas, but here we are discussing independent ones. Propositional logic is compositional, means that each part, it is a component. So each sentence is composed of smaller elements, and the meaning of those elements you have to define clearly. So meaning in the propositional logic is context independent. This was a good point. Unlike natural languages, because natural languages, they depend on the environment, context, where the words are spoken. So I have given you example. Saying someone sit down, saying in a soft tone and saying in a loud and harsh tone have different meanings. Whereas in this language, you say some sentence in propositional logic in any manner, it has the same meaning. So propositional logic overall has limited expressive powers because you cannot say something like pits cause breezes in adjacent square. It's very difficult to say. Or if you want to say that all the cells of Wumpus world, they are free of pits. There are no pits. So I gave you example. You will do it like this. You will write the names of all the cells. So let's say cell 1 1 and cell 1 2, all of them, and last one is cell 4 4. All of them together they imply no pit. Okay, like this you will do it, and I gave you the reason last time. If you have 1000 cells, this is very difficult to manage. It's not feasible. So for this purpose we use a new language over here. We go from propositional logic to a new language which is called first order logic. We will only discuss it briefly, very briefly. In this language, what we do is that I will give you first of all examples, and then we will discuss the details. Okay, so here is an English sentence: all men are mortal. Mortal means will die. Kullu nafsin dha'iqatul maut. Okay, so here it is, will die. So all men are mortal. So this thing that is in English, it is written over here in the first order logic like this. This over here, the symbol that you see, it is called for every. Okay, for every x, where x belongs to the class man. So when I write like this, man and x, it means that x belongs to the man class. So x is an element. X is an element. It belongs to man class. So man is a class. And when I write like this, man brackets x, it means belongs to, or it is, x is a man. So for every x which is a man, it implies, so it is the same implies that you had in the previous language. Most of the things from the propositional logic, they are used over here also. Okay, so same implies. So every x that is a man, it implies that x is mortal. So x belongs to the mortal class. Mortal class means that it is a class. So mortal class means that this class defines the meaning, just like in the previous chapter you defined the symbols and the meaning of the symbols. Here you define functions or classes, and you define the meaning of those classes also. So here the mortal class means that they will die. So all the members of this class, they will die. So we just say that x belongs to this class. That's it. So we say that if x belongs to man, x belongs to mortal. Okay, so think over it. If you are not clear, make sure you ask questions at this step. Another one, another English sentence, and it's equivalent in first order logic. So remember, first order logic is same as predicate logic we discussed before. Same thing. Predicate logic, another name first order logic. Okay, it is more advanced than the propositional logic. So another sentence we want to practice is everybody loves somebody. Okay, so everybody, we will define it by this: for every x, so there is this symbol, every. Now I introduce another symbol. It is this one. It is called for some. So that was all, every. and the other symbol is sum. Okay, so this second symbol you see for sum. So for every x there is some y where there is this relationship. There is a class loves x comma y. Okay, so for every x there are some y. So if x belongs, for example, x represents all the humanity, 7 billion people. Okay, so for every x there are some y. There are some people, father, mother, brother, sister, some people belonging to that category, not all. So there are, for every x, for whole humanity, there are some y or some people which they love. So this is the explanation. So here you see the use of x and y with these two operators. So this language has only these two operators, every and some. So these two operators, they just behave like you can say like for loop maybe, because they can work on many examples. Okay. There is one more example given here, but this one is we will cover it later on. It's difficult. So next we now go. So first order logic. If you remember previously, the propositional logic, it is assumed that the world contains facts. Okay. So we discussed that the world, at that time we discussed some of the facts. Okay. And we said that P means that it is hot. Okay. So whenever it is hot, P will become true. Whereas the first order language, it assumes that the world contains many things, not only facts. So over there, either it was true or false. World had some fact that is true or false at that time. Here we can have more things. At that time, if you remember, when we discussed the bad points, the drawbacks of first order, the propositional logic, we said that first order logic cannot describe things, objects. For example, cannot describe the age of a person. Okay, so here we can have these things. So first order logic, it assumes that the world contains, or world can contain, objects like people, house, number, color, and it can contain relations of those objects with some values. So color can be red, shape can be round, a number, it can be prime or even, or a relation, brother of, bigger than. So these things are there. In this language we have objects and then there are relations. And then we can have functions we can define. In the last example you saw previously, there were functions like mortal, function like loves. So here we can define any function, even mathematical functions, square root, plus. Okay. So we can describe over here many things. For example, we can describe now squares neighboring the wumpus, they are smelly. Squares neighboring a pit, they are breezy. So these things were not doable in propositional logic. Here it is possible. Also we can explain, we can say that for example, all the cells in wumpus world, they are free of pits. There are no pits. So what is the syntax? So remember, we will do the same thing as we saw previously, syntax then semantics. So syntax, it is a little bit tricky, difficult. Over here in the first order logic, there are two things that are given. Some things are provided by the user gives it. Some things are given by the language. In this case, the language, we write first order logic. Okay. So what user provides? User provides these basic things. Primitives means basic things. Basics. So user will provide, or user will define any constants. in that language you had only two constants, true or false. Here you can have any number of constants. You can define anything as constant. You can define, for example, 3 is a constant. So user will define constants. Okay. You can define name like Ali. It is a constant. Then you can have function symbols. After constant symbols, you can have function symbols. You can map the individuals to the individuals. So for example, Mary and John. So two persons. So you can define a function over here. So this is a function father of. You define this function. This function will connect two objects. So over here you see these are symbols, constants, or you can say they are objects, and the relationship is defined between them using a function. So mapping of the individuals to individuals is done using function symbols. So color of sky is blue. So color of is the relation that is done between sky and blue. And then the third one is predicate and relation symbols. Sometimes you over here the function symbols, they are the functions that return you either the output is true or false. So if Mary and John, they have a father-daughter relation, then it's true. If no, then it's false. Whereas the relation symbols, also called predicate symbols, they are such functions which return a value. So whenever I write, for example, color of apple comma green, so it will return me true or false. But I can also write it like this: function green and apple, is it true or not? So over there the mapping was done from one individual to another individual. Okay, the relation between one object and another object. Whereas in the relation symbol, the mapping is done from an individual to the truth value. So what is the truth value that makes this? That is the value of this symbol or this object. So apple, it's green, so we map it to the green value. So it can be done in two different ways. Okay. So these are the three things provided by the user. So user provides constants, function symbol, and then the last one is relation symbol. Clear? So this is it. This is the first part, three things given by the user. Now what the language provides? The first order language, it supplies these three basics or primitives. It will provide us variables to use. So we can define variables in this language. Constants, I can choose any constant name, any constant. So either a number or a name or anything. Similarly, I can define any function symbol and any relation symbol. It's up to me. I will also define the meaning. Whereas these things are defined by the language. So variable, it will have a special syntax. Like in programming languages, for example, you can define a variable like x or x9. But in languages you are not allowed, you already know. In programming languages, you cannot define a variable like 9x, not allowed. Variable should always start with alphabet. Same rules over here. Okay. Then there will be variables. Then there is a second thing which is called the connectives. Now these connectives are same that were in propositional logic. So 4 connectives. I would say there is fifth one. Where is not? So I think not is also there. They missed it. So not is also there. So they are same as in propositional logic. We call them connectives over here. They connect things. Okay. There is one more thing in this language. The third one, it is called equality. Equality is not same as equivalent. Equivalent is different thing. Equality is different. Equality, we will see it is used to assign some value to something. And the last one is the quantifiers. We saw the two examples, every and for some. The proper name for these are, every is called universal for all, and this other one is for some, it is called existential. There exists. Existential comes from there exists. Okay. So based on these, so there are four basics or four primitives supplied by the language. 3 by the user, 4 by the language. So a valid or legitimate means correct. So a correct expression of predicate calculus, we call it a well-formed formula or WFF or a sentence. So if a sentence is correctly created, so a correct expression in predicate logic or predicate calculus. So we also call it predicate calculus because its rules are more like used in the calculus in mathematics. So we call the sentence, the word sentence you have already seen. The sentences over here in this logic language, they are also called well-formed formula. So a typical exam question. Another name for sentence in FOL, first order logic, is well-formed formula. Clear? So you have seen these quantifiers. So you have four things that we saw previously. First order logic provides variables, connectives, equality, and quantifiers. Quantifier means it comes from the quantity. Okay. So quantify means to count. So it comes from quantify, to count. So universal and existential, they are related to counting. So quantifiers, universal and existential, they allow us to express properties of collections of objects instead of enumerating objects by name. So we can explain something on the whole objects, a whole set of objects. So we can express the properties of collection of objects, not only one object or not on the set created by me. So instead of I write that all the cells have no wumpus, no pit. So instead of collecting it like that, this is bad. I can write that all the cells operator universal to say something about all the cells. So it allows me to express something or some property of all the things or collection of things. So how it is done? It's very easy. You use a universal symbol followed by the variable that is used in the sentence. Okay. So I say universal variable. So I say, for example, universal x, and then I will write my sentence where x is used. So for I say for like this, for all C, where C are the cells, I will say that C implies no pit. Okay. Then I have to define somewhere over here what is C. C, I will say it is a cell. So for all C where C belongs to cell C. So I will do it same as there was previously in the examples. Where is it, that example? I think this one. For all X belonging to man class, it implies they are mortal. So same thing I will do over here. How I will do it? I will say, yes, I will do like this. For all C belonging to the cell class, I will say that there is no pit. Okay. Then the same thing can happen with the existential. Only difference between universal and existential is that existential is sum of the elements, whereas universal means all of them. So I can define another one for, no, this one, for some cells where for some C where C belongs to the cell class, it implies that there is wumpus. There is wumpus, or I can define wumpus class also. Okay, so here is the example. I can have constants. So remember, constant is defined by the user. Okay, user can define any constant like a symbol. It can be a wumpus, ali, anything, any name. It can be a constant, the symbol that I define. So each constant symbol names exactly one object in the universe of discourse. Remember, I cannot describe two objects with the same name. Now this is not allowed. If I want to discuss two people, I cannot have both of them with the same name Ali, because it's very obvious. If both of them have the same name, then I cannot identify them or I cannot call them separately. Okay, it is same as if I have two students with the same name, then I will be using the complete name of those students to call. Still I will try to keep them unique. So not all the objects they have so this is the case, but not all the objects they have symbol names. Some objects may have several symbol names. This is possible. Yeah, so if there is a person, I can have that person call it by name Ali, or I can call that person with the name student, or there can be many symbols attached to one object. It is possible. Okay, but it is not possible that one Ali name it is attached to many people. So normally the rule is that the symbols that you will define, it should be capitalized. What does it mean? It means the first letter is capital of all the words. After the symbols we saw variables. Now variable is something that is defined by the language, first order logic language. So it is used to define, used to represent objects or properties of objects. So without explicitly naming the object. Okay, normally we keep it lowercase. All of them are not capital, small. So example is I can define variable x, father, square, many names can be there. Variables, remember, they can change, their values can change. That's the important difference. Whereas constants, they are fixed, they never change when you define. Then comes the relation. So relation can be defined as, relation can be defined as two of them. So relation can be defined as over here, this one, relation symbol, it's a function. So relation is like a function where you give some input object and it will give you some, it will map it to a value. Okay, so relation is normally used to represent a relation in the universe of discourse. So relation is normally used to make a mapping between object and truth value. What can be the value of that object? So for example, relation I define between term 1 and term 2, it will be either true or false based on if the relation holds or not. Okay, so let's say I want to define this sentence, Malik, Imam Malik, he wrote Mauta. So I can write a function wrote Malik Mauta. Okay, so over here is the object Malik, and Mauta over here is the name of the book. It will be the value. Similarly, I can over here say that this is the course code. So instructor class, so instructor is the relation I want to check, course code and the name of the person who is teaching it. Clear? So this was the relation symbol. The function symbol is the other thing. Remember we discussed user provides these things. Go back. User will provide constants, function symbol, relation symbol. So relation symbol are also called predicate symbols. So function symbol is basically that it maps objects, creates the relation between object to another object. So object 1, object 2. So relation can be father and daughter relation can be shown. So I have two names given. So it can be written that, or maybe there is one person is Ali and other is Ahmad, and relation can be shown that Ahmad is the father of Ali. So father of can be used, father-son relation. So functions, they talk about the binary relation of the pair of function symbols. They talk about the binary relation of pair of objects. Both of them are objects, this and this. Whereas in the relation symbol, one was object, the other was value. So for example, the father relation might represent all pairs of persons in father-daughter or father-son relationship. So I can refer it like this also. Father, for example, father Ali, it gave me the name of the Ali's father. Father X, it will refer to the X variable's father. So here are some of the examples, some simple examples we will do over here. These are not examples, these are properties. So this over here is the property of first order logic. If you want to write for all X, all Y, you can change the order. So you can say maybe they are like commutative. You can change the order, it is same meaning. Okay. Similarly, if the operator is same, both of them are same, they can come in any order. X comes first or Y comes first, same thing. Similarly, for some X, some Y, you can say that for some Y, some X, no difference, same. But if the symbols are different, then the meaning changes. Be careful. Now you cannot write them in the opposite. So you write over here for some X, there are all Y. So it is not same as for all Y, there are some X. So even in English, you can clearly know it is not the same meaning. So here you are talking about for some X, there are all Y. Here you are talking about for all of the X, for all of the Y, there are some X. So meaning very tricky. Be careful. Next one over here, for some X, all the Y loves XY. So this is the example of this one. So there is a person for some X. For some X, so this sentence in English I will say that it means there is a person who loves everyone in the world. Okay, so it is this thing described. There is some person X who loves everyone in the world. Whereas if I write it in the opposite, Y comes first or universal comes first, then for all Y there are some X. Okay, so it will be interpreted as everyone in the world is loved by, or everyone in the world loves someone by at least one person. So it is not the same meaning. One person loves everyone in the world, or everyone in the world is loved by some persons. It's not same meaning. So I hope it is clear. Be careful about it. And finally, there is the duality relationship. Should we go to that side? For every x, everyone likes ice cream. Not of every x not likes ice cream. So what they want to say over here is, you can think over it if it makes sense to you. For every x, this is one part, x likes ice cream. So for every person, so every person in the world likes ice cream. So you can write it same thing. It's same as you say that there is, so you change the every to some, there is inverse not, and then there is some. So some, there are not some people who don't like ice cream. So English is tricky again, but it is the same meaning. There are not some people who don't like ice cream. So means that there are no people who don't like ice cream. It is the same as you say everyone likes ice cream. So whenever you see over here the universal, you can replace it with not of existential, and also you will have to change this symbol, invert it, likes, make it not likes. The meaning is same. So same thing as repeated. Some x they like broccoli. So this is a vegetable, broccoli. So some x they like broccoli. So you can say that not everyone don't like broccoli. Not all of them don't like broccoli. Maybe someone they like it. So it's the same meaning it comes. So remember, you change the invert the symbol, put a not, and put also a not before the function or relation symbol. Okay, pause it, think over it. So this is it, the place where we finish our course. It is slide number 12. I think this is enough from this topic, and I hope it is clear. If it's not clear, please ask question in the groups. So we finish over here. Make sure that you practice well, especially these numerical type questions for your exams. So I wish you all good luck for your break and the holidays, and after the holidays the exams.